Hi, I'm going to talk to you about this topic that is quite subtle in Newton's laws, and I want to take this step by step and explain this properly. So, consider this situation: you have three boxes. One is 2 kgs here, one is 1 kg, and the other one is 3 kgs. Okay, we are going to take this one by one and explain each of the situations. I have just, for the first part of this problem, I've taken only this red box and say since it is 2 kgs, and if you consider the acceleration due to gravity to be about 10 meters per second square, you have this force of gravity acting here. This would be mg, and this will be the reaction force due to this ground on which this whole thing is standing. And if you want to run Newton's laws, it is very simple. We are considering a force of 18 Newton acting on this in this box, this red box, and it has a mass of 2 kgs. And it is not, as of now, this blue and this green one has nothing to do with it. So the acceleration produced here is simply F by m, because F is equal to ma, and you have 18 Newton divided by 2 kg, which gives you 9. So if a force of 18 Newton acts on this box, you can be rest assured that it will have an acceleration of 9 meters per second square. This is part 1, very easy to follow. Now I'm going to part 2 now, and I'm going to get rid of these black ones, the black arrows that were here, the vectors that is showing the vertical forces, because we'll be considering only the horizontal forces. Because this is a 0 degree plane, which is a horizontal plane, there is no net force in the vertical direction, only forces in the horizontal direction. Now let us consider the same force of 18 Newton acting now on this red box. Say I am pushing that red box. Now it is in contact, it is already in contact with this blue, and let's say that this thing is stuck together. Okay, now let us look at the situation once more. So you have a force of 18 Newton, but because these two things are stuck together, the net mass of the system on which this 18 Newton is acting, you take the net mass to be m1 plus m2. In this case, it is 2 plus 1, that is equal to 3 kgs, because the blue one is here 1 kg and this one is 2 kg. So now if I look at the entire the whole system, I'm looking at the system as a whole, and I'm saying that there is a force of 18 Newton acting on it. And um, uh, if you look at the acceleration of such a system, it's simply going to be the net force divided by the net external force. That's very important. Net force, and it must be the net external force. And this force of 18 Newton is the external force that is acting from outside. I have shown it here on the center of mass because all forces behave as if they are acting on the center of mass. So it is technically, it is a net external force, and the total mass being 2 plus 1, and therefore you have 18 Newton divided by 2 plus 1 equal to 18 by 3 equals 6 meters per second square. Now look at the difference between this one and the previous one, where it was 9 meters per second square. This one is a very rather easy problem. This one, when it stick together, it gets a little complicated, and we'll see how. Now this 6 meters per second square is the acceleration of this red one and of this blue one. That's very important to remember. Okay, so now I'm going to now consider the following. I'll just take these sticks out so that it's easy for me uh, um, to write further. What this F is equal to ma equation that I have written right here, this is of the entire system consisting of both m1 and m2 and an external force of 18 Newton. Please note that although it is shown on the center of mass of red, it is an external force. It is shown on the center of mass of red because all external forces behave, the system behaves as if all the external forces are acting on the center of mass. Now let's look at only the red system, where you run the equation F1 is equal to m1 times a1, And then you're looking what is the net. We know that the acceleration is 6 meters per second square, which is non-negotiable, which we've already got from the previous argument up here. And we know that the mass of it is 2 kgs. So you multiply these two together, you end up getting 12 Newton. This means that for an object of 2 kgs to be accelerating at 6 meters per second square, it requires only 12 Newton. But then there is 18 Newton acting on it already. So where is there is a disparity of 6 Newton. Where did this come from? So this is where, because it is in touch with another object, and I'm going to bring this vector here, and it is in touch with another object, which is this blue object. The only logical sense is that there is a 6 Newton acting in the opposite direction, right? And then therefore I'll change color and write this as 6 Newton. Now where did this 6 Newton come from? Surely it came from the contact that this red body has with the blue body. And as you can see, this red body is pushing this blue body, and if there is a 6 Newton here, there has to be a 6 Newton here. This is equal and opposite. This is the third law of Newton. So now if you run the equation for the second object here, F2 is equal to m2 times a2, you know that the acceleration is 6 meters per second square. That is non-negotiable. Multiply that by 1 kg and you get 6 Newton. That means there is a 6 Newton acting on this blue object, which is here. Where this force come from? This came from this red object pushing this blue object, and because the red is pushing the blue is pushing back at the same rate, equal and opposite, 6 Newton here. So therefore you see that this 18 Newton in one direction, 6 Newton in the opposite direction, they are opposite, so they subtract and give you the 12 Newton. So F1 is equal to M1A1 works, F2 is equal to M2A2 works, and the net of the system, where the F net equals M net times the net acceleration of the system, also works. All three. I'm going to push this argument further and then add the third mass to it now. Let's take the same situation where the same 18 Newton is acting on the red object. And now the difference is that the red, blue and the green objects are all in contact and they're all, say, sticking together. Now let us ask the question. F equal to 18 Newton. This is the net force acting, net external force acting on the system. There is no other external force. Again, remember, I'm showing this on the center of mass of red because an external force will act and the system will behave as if the external force is acting on the center of mass. So here you have the net force, which is 18 Newton, and the net mass in this case is going to be 2 plus 1 plus 3, which is equal to 6 kgs, and therefore from F net equals m, well, I could say m net multiplied by a net is going to give me 6 kg times a, and since a is F is 18, you know that the acceleration is surely going to be equal to 18 divided by 6, which is equal to 3 meters per second square. So when you have an 18 Newton force acting on a system with 6 kgs, surely the acceleration will be 3 meters per second square. Now let us take one by one. Now in these equations that I have written, I have taken the system as a whole, and now I'm going to take each of these boxes one by one. First the red one, F1 equals M1A1. This acceleration of the system is non-negotiable. So we have 3 meters per second square, and you multiply that by the mass, which is 2 kilogram, and then you end up getting 6 Newton. This is the net force on object number 1. But then there is a 18 Newton acting on it, we know. So the only way in which the net can be 16 is if there is an opposite force. If there is an opposite force acting against the against the 18 Newton, like this, and for the net to be 6, this has to be 12. Oh, I should write that in blue. So I'll write that in blue and call this 12 Newton. Now you know that the net is this. Now where is this 12 coming from? The only way that the 12 can come is from this blue object which is in touch with the red object. So I'm going to put this one here, right? And I'm going to call that surely 12 Newton. And these two blues, this blue and this blue, they are action reaction pairs, and so they are equal and opposite. Now take this, so the F1 is done. Now let's look at F2 is equal to m2 a2 is 3 meters per second square, which is non-negotiable. M2 is 1, so the net force is going to be 3 Newton. But then there's already a 12 Newton acting here, so that would mean that there must be another force acting on the center of mass like this, and I will bring this forward, and that for the net force to be 12, the only way that is possible is that this force is 9, sorry, for the net force to be 3, the only way that's possible that this green one is 9 Newton. Now where did this green one come from? Well, it came from this green object right here. It must be equal and opposite. We should also draw it to scale. It's not perfectly to scale, but that's here. This should be 9 Newton. Now let us check F3 is equal to m3a3 must be equal to 3 kgs times 3, which is equal to 9 Newton, which is consistent with what we've got. The point that is very subtle about Newton's laws, and I'm going to write that down here, is the fact that when you have three systems, one, say two, and they say three, I know that this is not exactly as we had drawn it earlier, but you have three different objects, say, F is equal to ma will hold for this object alone, for this object alone, for this object alone. F is equal to ma will also work for these two objects alone, these two objects alone, and F is equal to ma will work for this entire thing taken as a system. So depending on how you change the system, whether you are taking the system to be a single object or two objects or three objects, your F is equal to ma will always work, provided F is considered external, right? And mass is the total mass of the system that you are considering. So in these three examples, and especially in this example, as you can see, all three are satisfied very well, and the net is also, see, F1 is equal to m1a1, F2 equals m2a2, and F3 equal to m3a3, and the F net must also be equal to m net into a net. This is the idea.